Ground rod resistance is a critical factor in ensuring electrical safety. A ground rod provides a path for fault current to safely dissipate into the earth, protecting people and equipment from electrical shock. The easiest and cheapest method for checking the resistance of a ground rod driven into the ground involves the use of a multimeter. A multimeter is a versatile electronic instrument that can measure voltage, current, and resistance. For ground rod testing, we're primarily interested in its resistance measurement capability. Here's how to perform the test effectively. Firstly, understand the purpose of ground rod resistance testing. A low resistance to ground indicates that the ground rod can effectively dissipate fault current. Electrical codes, such as the National Electrical Code, typically specify a maximum acceptable resistance value. While the NEC doesn't mandate a specific resistance value, it references other standards like IEE 142, which recommends 25 ohms or less. However, many feel that 5 ohms or less is a safer and more effective value. The lower the resistance, the better the ground rod's ability to protect against electrical hazards. Secondly, gather the necessary equipment. You'll need a multimeter capable of measuring resistance, 2 auxiliary ground rods, also known as test probes, and insulated test leads. The auxiliary ground rods should be metal rods, typically 4 to 8 feet in length, that can be driven into the ground. The insulated test leads are used to connect the multimeter and auxiliary ground rods to the ground rod under test. Thirdly, prepare the test site. The ground around the ground rod should be moist, but not waterlogged. Dry soil can significantly increase resistance readings, leading to inaccurate results. If the soil is dry, you may need to water the area a day or two before performing the test. Clear any debris or vegetation from the area around the ground rod to ensure accurate probe placement. Fourthly, set up the test configuration. This involves using the fall of potential method, a 3-point test that provides a reliable resistance measurement. Drive the ground rod under test into the ground. This is the main ground rod that you want to test the resistance of. Further away, the auxiliary ground rods are placed from the rod to be tested, the more accurate the test will be. Place one auxiliary ground rod, let's call this cone, to distance of approximately 62% of the distance between the ground rod under test and the second auxiliary ground rod, call this cone. Place cone at a distance of at least 20 feet from the ground rod under test, but ideally further if space permits, to minimize overlapping spheres of influence. The key is to place all 3 rods in a straight line. Fifthly, connect the multimeter. Disconnect the ground rod under test from the electrical system to isolate it for testing. Connect one test lead from the multimeter to the ground rod under test. Connect the second test lead to auxiliary ground rod pole. Set the multimeter to measure resistance, typically denoted by the omega symbol. Sixthly, take the resistance measurement. The multimeter will display the resistance reading in ohms. Record this reading. Seventhly, verify the measurement. To ensure the accuracy of the reading, move auxiliary ground rod pole a few feet in either direction along the line between the ground rod under test and auxiliary ground rod cone. Take another resistance measurement at each new position. If the resistance readings are relatively consistent, the initial measurement is likely accurate. A significant variation in resistance readings indicates that the auxiliary ground rods may be too close to the ground rod under test, or that there may be underground metallic objects interfering with the test. Eighthly, interpret the results. Compare the measured resistance value to the acceptable limits specified by relevant electrical codes or standards. If the resistance is above the acceptable limit, the ground rod system may need to be improved by driving additional ground rods or using ground enhancing compounds. Ninthly, consider alternative testing methods. While the multimeter method is the simplest and cheapest, it may not be the most accurate in all situations. More sophisticated ground resistance testers, such as clamp-on ground resistance meters or 3-point fall of potential testers, can provide more accurate results, especially in areas with high soil resistivity or underground metallic objects. Tenthly, understand the limitations of the multimeter method. The accuracy of the multimeter method can be affected by several factors, including soil moisture, soil composition, and the presence of underground metallic objects. The method is best suited for situations where a quick and approximate resistance measurement is sufficient. For critical applications or where high accuracy is required, a more sophisticated testing method should be used. 11thly, perform regular ground rod inspections and testing. Ground rod systems can degrade over time due to corrosion or changes in soil conditions. Regular inspections and testing can help identify potential problems before they lead to electrical hazards. The frequency of inspections and testing should be based on environmental conditions and the criticality of the electrical system. 12thly, document the test results. Keep a record of all ground rod resistance measurements, including the date, time, location, and test method used. This documentation can be valuable for tracking changes in ground rod performance over time and for demonstrating compliance with electrical codes and standards. 13thly, implement ground improvement techniques if necessary. If the ground rod resistance is too high, there are several techniques that can be used to improve it. Driving additional ground rods in parallel can reduce the overall resistance. Ground enhancing compounds can be added to the soil around the ground rod to improve its conductivity. Replacing corroded ground rods with new ones can also improve performance. 14thly, ensure proper grounding system design. The effectiveness of a ground rod system depends not only on the resistance of the ground rod itself, but also on the overall design of the grounding system. The size and type of grounding conductors, the bonding of metallic objects, and the location of ground rods all play a role in ensuring electrical safety. 15thly, understand soil resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Soils with high resistivity are more difficult to ground than soils with low resistivity. Soil resistivity varies depending on soil type, moisture content, and temperature. Areas with high soil resistivity may require more extensive grounding systems to achieve acceptable resistance levels. 16thly, consider the impact of underground metallic objects. Underground metallic objects, such as pipes and conduits, can affect ground resistance measurements. These objects can act as parallel paths for current, leading to inaccurate readings. When performing ground resistance tests, it is important to be aware of the presence of underground metallic objects and to take steps to minimize their impact on the measurements. 17thly, be aware of seasonal variations. Ground resistance can vary seasonally due to changes in soil moisture and temperature. Resistance is typically higher in the dry season and lower in the wet season. When interpreting ground resistance measurements, it is important to consider the time of year and the prevailing weather conditions. 18thly, use appropriate safety precautions. When working with electrical systems, it is important to follow all applicable safety precautions. Wear appropriate personal protective equipment, such as gloves and safety glasses. Disconnect power to the equipment being tested before making any connections. Never work on live electrical circuits unless you are properly trained and authorized to do so. 19thly, seek professional assistance if needed. If you are not comfortable performing ground resistance tests yourself, or if you are unsure about the results, it is best to seek professional assistance from a qualified electrician or grounding specialist. These professionals have the training, experience, and equipment necessary to perform accurate ground resistance tests and to identify and correct any grounding problems. 20thly, understand the importance of bonding. Bonding is the process of connecting metallic objects together to create a low impedance path for fault current. Proper bonding is essential for preventing electrical shock hazards. All metallic objects that are likely to become energized during a fault should be bonded together and connected to the grounding system. 21stly, consider the use of exothermic welding. Exothermic welding is a process that creates a permanent, low-resistance connection between metallic conductors. This type of connection is often used for grounding systems because it is more reliable than mechanical connections. Exothermic welds are resistant to corrosion and can withstand high fault currents. 22ndly, be aware of the requirements for sensitive electronic equipment. Sensitive electronic equipment, such as computers and medical devices, may require special grounding systems to protect them from voltage transients and electromagnetic interference. These grounding systems may include isolated ground circuits, surge suppressors, and shielded cables. 23. Understand the different types of grounding systems. There are several different types of grounding systems, each with its own advantages and disadvantages. The most common types of grounding systems include the solid grounding system, the resistance grounding system, and the impedance grounding system. The type of grounding system used should be selected based on the specific application and the requirements of the electrical system. 24. Consider the use of ground fault circuit interrupters, or GFCIs. GFCIs are devices that detect small amounts of current leakage to ground and quickly disconnect power to the circuit. GFCIs are an important safety device for protecting people from electrical shock hazards. They are typically required in areas where there is a high risk of contact with water, such as bathrooms and kitchens. 25. Understand the role of the equipment grounding conductor. The equipment grounding conductor is a conductor that connects the non-current carrying metallic parts of electrical equipment to the grounding system. This conductor provides a low impedance path for fault current, helping to prevent electrical shock hazards. The equipment grounding conductor should be properly sized and installed in accordance with electrical codes and standards. The described procedure provides a cost-effective approach to assess ground rod effectiveness.